Vectors. Today we're going to talk about vectors. A vector is a quantity that has both length and direction. Take a look at the picture there. A is the initial point. B is the terminal point where it stops. You might think of this like a ray, but it's not like a ray. It actually has a finite size, meaning it's limited. It has a certain length. So I'm going to call A the tail and B the tip, because most of the time, rather than use 2 points, you could use 2 points to describe a vector and call it vector AB. Most of the time, we use a single letter to describe the vector, like vector V, and we put it in what's called component form. Component form has the initial point, the tail, at the origin, and we just use a single point to describe it. It doesn't matter where a vector is in the coordinate plane. What matters is its length and direction, because a vector is a quantity that has both length and direction. You heard me just say it. It doesn't matter where a vector is in the coordinate plane. You can put it anywhere. All that is important is the direction and the magnitude. That's the length of the vector. Most of the time, we put it in what's called component form. Component form uses the greater than, less than. This is like an ordered pair. Remember, we're describing it with a single point, the initial point being at the origin. It's just like an ordered pair, except we use the greater than, less than. So how do we find this vector in component form? If we have 2 points, all we do is we take the tip minus the tail. So here's the tip. Here's the tail, the back part of it, and we take the points 2, 4, the tip, minus the tail, that's -4, 2, and that gives us the vector in component form, and you just subtract those like you think. You go 2 minus -4, which would be 6, put a less than there, comma, 4 minus 2, which would be 2. So this is the same exact vector in component form. Let's look and see what that looks like. Notice how the vector I just put in black here has exactly the same length, goes exactly the same direction, but now we can describe it with a single point, knowing that its first point, its initial point, is at the origin. We can add vectors visually in the coordinate plane, but we can also add them algebraically, and it turns out to be very simple. Notice the vector in red. The endpoint is 1 for x and 4 for y. I can add that to the vector in blue. Notice these are in component form. Your initial point is at the origin. The vector in blue is the vector 5, x is 5, and y is 1. And adding those works just the way you think it would. 1 plus 5, hey, that's 6. 4 plus 1, that is 5. So these two vectors make a vector. By the way, this is called the resultant vector. 1, 4, and 5, 1 do together. It does what the two do together in one motion. Observe, if you take and do the red vector, now the way you add them is tip to tail. I'll take the blue vector and slide it up. Notice how I'm placing them tip to tail. First, we travel along the red vector, and then we travel along the blue vector, and we end up at the point 6, 5. And the resultant vector, 6, 5, is the vector in one motion, does what those two do together. Here you can see the resultant vector with initial point at the origin, ending up at the point 6, 5. And the order I add them in does not matter. I could do the blue vector first, travel along the vector 5, 1, and add that to the red vector, then travel the red vector, which is 1, 4, and I would still end up with that same vector, the resultant 6, 5. Think of the resultant vector as the one vector that does what the two do together. The sum of the two create that resultant vector, and it's one motion instead of two. The direction of a vector is described by the angle formed between the x-axis and the vector, this angle right here. When you find that angle, you're going to use trigonometry to do that. You'll imagine this triangle where this is 3 and this is 5 and this is your x degrees you're looking for. And I know to find x, I use the inverse function. And looking at x, it's opposite over adjacent. So that would be the tangent. And we're finding an angle. It's the inverse tangent. The inverse tangent of opposite over adjacent equals that angle I'm looking for. It's the x, or x degrees. Go to your calculator, make sure you're in degrees, not radians, and do the inverse tangent to find your direction. So our direction is an angle, and I'll round to the 10th. Notice the 6. We'll bump the 9 to a 10, and I'll have to carry it. Looks like that angle is 31 degrees, 31.0 degrees. You do not need to put the 0, but a lot of times you do because that shows that you rounded to the 10th. The magnitude of the vector is the length of the vector. You can just look at the picture and use Pythagorean theorem, or you could use distance formula, remembering that the origin is the point 0, 0. Your choice. But I would probably just look at this and say that, we'll call this C, that 3 squared plus 5 squared equals c squared. That's 9 plus 25 equals c squared, which is 34. C squared equals 34, and then I can take the square root of both sides. If they ask for it exactly, you could say, hey, it's exactly root 34, because that can't be simplified. If they ask for it to the 10th, then you just punch that into the calculator, and you'd get about 5.8. So the length of the vector, the magnitude, is about 5.8, or root 34 exactly, and the direction is 31 degrees. Our first example is question 3. When we write a vector in component form, remember the initial point is at the origin. Take a look at this vector I've given as an example, the vector 5, 3, initial point at the origin. Notice how the vector 5, 3 has an x of 5 and a y of 3. And it doesn't matter where I put that vector. If I put it up here, for example, I would still go over 5, 1, 2, 3, 4, 5, and then up 3. And so this vector right here would still be the same vector. It would be the vector 5, 3. It doesn't matter where that initial point is. I will still travel an x distance of positive 5 and a y distance of positive 3. Here we have a vector on a grid, and you can look and tell what the vector would be in component form just by understanding what it does. Or just imagine that this point is the origin, and what would my vector be in component form if the initial point was at the origin? Well, observe how this vector travels down 3, negative 3, that's the y distance, and left 1, that's negative 1, that's the x distance. In other words, in component form, this would be negative 1, comma, negative 3. Question 4. Same idea as the last one. Imagine this is the initial point here, the origin. What would my vector be in component form? X would be moving to the left, 1, 2, 3, 4, 5. That's negative 5. And y would be traveling up, 1, 2, 3, 4. Positive 4. So in component form, my vector would have an x of negative 5 and a y of 4. Here we have a vector on a grid. We could figure out component form by doing tip minus tail. Notice the tip is the point 6, 2, and the tail is the point -3, -1. And if we do the tip, 6, 2, minus the tail, -3, -1, and subtract the corresponding coordinates, 6 minus -3 is +9, 2 minus -1 is +3. In component form, we get the vector 9, 3. Note that we can also figure that out just by looking and seeing what the vector does. The vector starts at J, travels this distance here for X, which is going to be 9, and this distance here for Y, which is going to be 3. We can see that in component form, the vector would be 9, 3. Question 7, very much like the last one. We have an initial point of 3, 4. And a terminal point of -2, -2. Again, we can do tip minus the tail and find that it is -2, -2 minus 3, 4 in component form. -2 minus 3 would be -5, and -2 minus 4 would be -6. And there's our answer. But we can also observe that if we start at point J, this vector would move down 6, that's -6 for Y, and left -5 for X. We can see, just looking, that this is in component form the vector -5, -6. Find the component form of a vector with initial point at 6, 9. So I have a coordinate grid somewhere, and I'm over 6, up 9. This is the initial point where we're starting, and a terminal point of 0, 4. So somewhere on the axis is where we're ending, and that is the point 0, 4. Now, we can find the vector in component form by just taking the tip minus the tail, and the tip is 0, 4 minus the tail of 6, 9. 0 minus 6 is -6. 4 minus 9 is -5. In component form, this is the vector -6, -5. Question 15. Graph the following point. It's in component form, so the initial point would be at the origin. The terminal point would be -3 for X and up 1. So we're going to start at 0, 0 and end at -3, 1. For question 18, if we were to do this graphically, we would place these vectors tip to tail, where one ends, the other begins. But since they're in component form, the resultant vector, the one vector that would do what these two do together, is just the sum of these two. We'll add the x's. -9 plus 8 is -1, and we'll add the y's. 1 plus -10 is -9. So the sum of these two vectors, the result of these two vectors, is the vector in component form -1, 9. Be sure that you enter the less than and greater than to identify that it is in component form. Question 23. Graph the following vector addition. In component form, we have the vector 0, 2. So we're starting at the origin. X is 0, y is 2, and we'll end up right there. From there, we're going to add to that the vector 6, 1. Now what that will do is move a distance of 6 for X, so over 6 and up 1. We're going a distance of 6 for X and 1 for Y. Notice that when I add 0, 2 plus 6, 1, if I add the x's, 0 plus 6 is 6, and 2 plus 1 is 3. The resultant vector is the vector 6, 3. The one vector that does what these two do together would be in component form the vector 6, 3. It goes an x distance of 6 and a y distance of 3. Question 24. What is the magnitude of the vector v with initial point A and terminal point B in the coordinate plane? There it is. The magnitude refers to the length. So what we need to do is find the length. Now, you could use Pythagorean theorem if you did a triangle and you counted 1, 2, 3, 4, 4, 1, 2, 3, 4, 5, 6, and you could go call this C or whatever you want. 6 squared plus 4 squared equals C squared, and find C, and that would give you the answer. Another way to do this is with the distance formula. The distance formula is the square root of x2 minus x1 squared plus y2 minus y1 squared, and you just plug in your 2 points. My ordered pairs are 2, -2, and -2, 4. So you'd subtract the x's, -2 minus 2 squared, and subtract the y's, 4 minus -2 squared. Notice that this is -4 squared plus 6 squared. Compare that to this. That will end up being 16 plus 36, which is 52. It says use radical form, no decimals please. That's where we have to remember our perfect squares. That's 4, 9, 16, 25, 36, 49, and so on. Any number times itself. The smallest one that divides evenly into 52 is 4. This is 4 times 13. We can take the square root of 4. That goes out in front of the root, so it would be 2. And 2 root 13 is my answer in simplest radical form. In question 26, we're going to find the magnitude and direction. The magnitude is the length, and you can just make that triangle in there. Right here, this would be 3, and the bottom of this triangle would be 3. This is our direction, call that x degrees. To find x, I see that we have an opposite and adjacent, and we're finding an angle. That means we use the inverse function. The inverse tangent of 3 over 3, which is the inverse tangent of 1, that would be x degrees. So we'll plug that in the calculator. We get exactly 45 degrees. The direction is 45 degrees. The magnitude would be the length of that. Pythagorean theorem we can use here, or the distance formula using the origin as one of the points. A squared plus b squared equals c squared is 3 squared plus 3 squared equals c squared, or 9 plus 9 equals c squared, which is 18 is c squared. We'll square root both sides. It doesn't ask for it in simplest radical form. It says to the nearest tenth. So the square root of 18 is about 4.24. So to the 10th, that would be 4.2. That's the length of that vector. Last question. This symbol here is magnitude. Sometimes you see it written as this. Notice the way it's only half an arrow. I've seen it like this, and I've seen it with 2 bars for magnitude. It's the way we did it in college. And either way, we're referring to the length of the vector. Notice how it's in component form. We have the initial point of 0, 0. And then we're going to go right 10 and up 4. So this is the point 10, 4. And in this triangle then, we have a height of 4 and an x distance of 10. And we can find the hypotenuse, the magnitude, call it c. We know that a squared plus b squared is c squared. That's 10 squared plus 4 squared equals c squared. 100 plus 16 is c squared. 116 is c squared, and we'll square root both sides, and we'll put that into the calculator. And it says round to the nearest tenth of a degree, and the magnitude is in simplest radical form. I took a list of perfect squares, 4, 9, 16, 25, 36, and so on. The first one I tried was 4, and I discovered that 116 is 4 times 29, and the square root of 4 is 2, so 2 root 29. That would be the magnitude. Now we're going to find the angle to the nearest tenth of a degree. My triangle's a bit ugly here, but this is the angle we're looking for, the direction between the x-axis and the terminal side of the vector. Call that x. We can see that we have the opposite and adjacent, which is tangent. The inverse tangent of opposite over adjacent, 4 over 10, is how I find my x. I got 21.80, so that's about 21.8 degrees to the nearest tenth.